And so here we are now on the flip side of the B test. Thoughts on it? I'm not really sure what my predictions are about cutoffs at this point. I do think they were harder than the A test, at least for the AMC 10. So 2022 AMC 10B problem 1, also the 12B problem 1. Define X diamond Y to be the absolute value of the difference. That's how you want to read that, okay? For all real numbers X and Y. What is the value of, and you're going to start with the parentheses, the absolute value of the difference is 1. So you get 1 symbol 1, and then you have minus the absolute value of the difference is 1 still. We don't care what it's negative, positive, it's irrelevant. This is going to be 0. The absolute value of the difference negative is 2, and you've got a minus sign, 0 minus 2, negative 2. Let's get to the next problem. Continuing now with the 2022 10B problem 2, also the 12B problem 2. They aligned for the first two problems. In rhombus ABCD, point P down here lies on segment AD, as you can see, so that segment BP is perpendicular to AD, meets it at 90 degrees. AP is equal to 3. We'll go ahead and label as we read. PD is equal to 2. What is the area of the rhombus? Note the figure is not drawn to scale, which is good because mine's off from there, drawing a little bit as well. But first things first, a rhombus has 4 equal sides. So side length of 5, this must be 5. 3, 4, 5. 5 times 4, 20. That's the area. The area of any parallelogram is base times height. So if your base is 5 and your height is 4, that's it. It works just like a rectangle in that way. Let's get on to the next problem. Okay, so for this problem, I just wanted to say it is not my solution. Actually, when I was doing my test solve, I did end up getting bogged down with this one and figured I was just missing something simple, so I skipped it and went on. And then I ended up not actually coming back to do it. I got down with my method of getting down to basically the one that had 1, 1, 1, 2, 1, 1, 1. I think, there was another 1 here and a 1 here. This one, which I called a sum of 10, and then the sum of 14 and the sum of 22. Those were the 3 that I got hung up on with just trying basic divisibility rules. So obviously we know that's divisible by 11. You know that this has a sum of the digits of 6, and since it's a multiple of 3, it's divisible by 3. I did all those kinds of rules. And it didn't actually play out because you got stuck with these sums here. And there's probably a way to get them, but I was just like, okay, I must be missing something simple. And later, when conferring with a friend, they pointed this out. They had seen it somewhere before. Let's see what it looks like. If you split this 2, right? So you have 100 plus 20 plus 1. So if you make it 100 plus 10 plus 10 plus 1, then if you factor out from this one a 10, 10 plus 1 plus 10 plus 1, you'll now see that you get, obviously, you can factor this out and you will get 10 plus 1 times 10 plus 1, meaning that there's a 1 right here. And since you're factoring out the parenthesis, you're left with this 10, this plus, and this 1. We already knew it was 11 squared, but this is just to show proof of concept. Let's go to the next one over here. This is 10,000, which is going to be 10 to the, this is 10 to the second. You have 10 to the fourth, plus 10 to the third, plus 10 squared, plus 10 squared, plus 10 to the first, plus 10 to the 0, or just plus 1 if you prefer. Okay, so this right here, notice what we did again. We split the 2 in the middle to two 10 squareds, right? Because it's basically 200, and so it's 100 plus 100 as well. And all we're going to do is the exact same thing. We're going to group these 3 and factor out the biggest power that we can, which is 10 squared, and you're going to get 10 squared plus 10 plus 1, and that's exactly what you have right here. So you'll have plus 1 times the same parenthesis, 10 squared plus 10 plus 1. So we're just going to factor that out, and you're going to have 10 squared plus 10 plus 1 times essentially 101, 10 squared plus 1. So that's going to keep going. If you check one more, you'll see that it works also. And in fact, all of these are going to end up working out to be factored just like this. Let's just see one more so you can see the pattern still going. So next one's going to have 10 to the 6th plus 10 to the 5th plus 10 to the 4th. And you'll have 3 terms and then your repeated one. The repeated one is now in the thousands place. So it's 1,000 or 10 to the 3rd. And then you're going to have a 1 times that 10 to the 3rd plus 10 squared plus 10 plus 1. And you're going to group these 3, factor out 10 to the 3rd. What are you going to have left? 3, 2, 1, 0. 3, 2, 1, 0. It's going to match. And it's going to keep doing that. And so in fact, there are no, how many of the first thing are prime numbers? None of them are prime numbers. You're going to get A. How do you think of this? They said they had seen something like it before. So if you hadn't have seen that before with some other contest or experience that you had had, maybe it was on an AMI or an AMC 10, if you know where this might have been seen before and you would like to leave it in the comments for other people to check out, that would be great. Otherwise, you're going to have to kind of get lucky on that one. Obviously, when you're getting to really big numbers, it becomes hard to do divisibility rules for all of them. The divisibility rule for 11 works for several more, every other digit something, but these 3 were a little bit harder for me to come up with. So if you got stuck on that one, don't feel bad. I did too, and you either knew about this or you drew the inference really quickly with a little bit of luck, some insight, something like that. But in the absence of that, this would have been a great problem to skip. Let's get on. Okay, so now the 2022 AMC 10B problem number 7, which was also the 12B problem 4. For how many values of the constant k will the polynomial x squared plus kx plus 36 have 2 distinct integer roots? Okay, so we need distinct, we need integer roots. Roots is when you set it equal to 0, the x-intercepts, the zeros, the roots, the solutions, that equation, all the same thing. So we can use quadratic formula because we don't know what else to do, and that's also going to give us some insight for how we can achieve integer roots. So let's get a look at what quadratic formula would look like. You're going to have negative k plus or minus the square root of k squared. That's your b squared minus 4ac, 4 times 36, 144, and a is 1, doesn't count for anything really here, over 2. Okay, so now what? That's your set of roots. These are the roots, right? X would equal this. And we want there to be 2 distinct integer roots. So let's think about that. This is going to have to be a perfect square. If it's not, you won't be able to square root it to a rational number, and irrational numbers are not going to work out to produce integer roots for x. So we're going to need, here is kind of the point where you're going to have to kind of think about how you're going to capitalize on that realization. So if I set k squared minus 144, I oftentimes when we're talking about integers, I'll put a capital I. Now, when I first solved, the first thing I did was, well, this is difference of squares, k plus 12, k minus 12. And then I started thinking about what k could be. How am I going to capitalize on this? So if I tried like 13, for instance, for k, I'll get 25 times 1. Hey, that works out because 25 is an integer squared. It's 5 squared. So I did this, right? So I said k is 13 and I is 5. So once you get the 5 value, you'd have like negative 13 plus or minus 5 over 2. Okay, great. So then I thought, okay, so now what? Do I just keep guessing checking? And I did that a couple times looking for some kind of pattern before you can kind of realize when you go to 14, you'll have a 26 times 2, not going to be a perfect square because there's no, think about it, you got 26 times 2. There's a 13 in here, right? There's no 13 over there. not going to work out. If you try 15, you'll get 27 times 3. Hey, that's 81. But I started to notice these numbers here. This is going up and up, which would mean 81 is a perfect square. That's great, but we're going to be at this forever. So abandon course. Right? Got to find a new way to go about it. So now we got to think differently. So if that's going to be something that's just kind of like a long path you travel down with no fruit, maybe we should go back over to here and think about how this is an integer. What if I move the 144 over? Let's make some conclusions here. K squared equals I squared plus 144. Now, what is I? An integer, okay? And what is 144? An integer. And when you add two integers, you get an integer, which means K must be an integer, but notice they didn't tell us that at the beginning. So you're gonna have to have an integer value for K, because no non-integer squared. Well, wait, what about square roots though? But you could have a square root squared to get an integer. Great, but then you're gonna, let's say it was like, for example, let's say that, I don't know, let's say that I was 1, and then K would equal the square root of 145. The problem when you plug that in, you don't get integer roots for X. So you can think that path, you gotta conclude then, okay, we can solidly say if that's irrational and this came out to be an integer, it's not going to work. Okay. Likewise, if this was an integer and that was irrational, it's not going to work. So with that in mind, we proceed. So if I got that thought from this, now what? I'm going to move the I squared over, because we did like that difference of squares action, but maybe there's a better difference of squares. So if I do K plus I times K minus I equals 144. Wait a minute. K is an integer. I is going to be an integer. Then K minus I will be an integer, and so will K plus I. And so with that in mind, we're going to erase here, and we're going to target 144. If I set K plus I equal to 144, and K minus I equal to 1. Notice that when I add down, I'm going to get 2K is 145, which is a problem because you're not going to get an integer for K. So since you're not going to get an integer for K, one more thing too, what about if K was a fraction? I kind of was thinking about it just now. If K was a fraction, then a fraction minus an integer would be a fraction, and a fraction plus an integer would be a fraction, and you're still not going to get an integer when you multiply those things. So think of it like, for example, 7 minus 3 over 2 times 7 plus 3 over 2. You're going to get 14 over 2, you're going to get 11 over 2 times 17 over 2. Not going to be an integer because you're going to have this fraction every time, right? So from there, we come over here, we say, oh, look at this. I noticed that when this is even and that's odd, problems ensue. We either need to have two odds that when we add, we get an even, so the 2K will divide and give us an integer value for K, or we need two evens. Therefore, all combinations, like 3 times 48, also won't work because they have an odd number involved. Could I have two odds? No, because two odds could never multiply to an even. Now we can solidly conclude we're looking for two even divisors. Let's try them out. 72 and 2 go up to 4. 4 times 36 go up to 6. 6 times 24 go up to 8. 8 times 18 and 12 times 12. Okay, so let's try this out. You're not going to get, as this number gets larger, you're just going to find these ones over here. So we don't need to look for any others. 10 doesn't go in. We're satisfied. This is all the cases to try. And notice that what this would mean, right? If I put this as 72 and 2, what am I going to do with these numbers? I'm going to add them and divide by 2. So in this case, K would equal 37. In this case, K would equal 20 because you're adding and dividing by 2. In this case, K is going to be 15. In this case, you're going to get K is 13. In this case, you're going to get K is 12. But the problem with that, let's just see what happens. At 12 minus 12 is 0. You do get an integer squared, but you get negative 12 plus or minus 0. Again, we needed that k squared minus 144 to be greater than 0. And also an integer so that we could simplify it. Okay, so with that in mind, we've now got these 4 values of k. And does k have to be positive though? Could k not have been negative? Let's see what would happen if I made this, negative 72 and negative 2, because those multiply to 144, then k would have been plus or minus 37. Notice it's not going to matter because you're going to be squaring it, so it's not going to impact anything. In fact, let's plug it in just to make sure we're not getting trapped by something. Negative 37 plus 12 is negative 25. Negative 37 minus 12 is negative 49. Notice that the product of the two negatives is a positive and they are both perfect squares. It would mean that the I value we're looking at is 5 times 7, 35. And you plug that in here. Think about what you get though. K is an odd number. This is good we checked. K is an odd number. There's so many different things to check in this problem to be sure you're feeling good. Odd, negative odd, doesn't matter. Plus or minus, and you're going to have 35. So it's like negative 37 plus or minus 35 over 2. That's negative 2. It doesn't say they have to be positive integer roots, just distinct. And when you add and subtract another integer, they're definitely going to be unique solutions. So what about the 20? No, now we have an even number. Okay, well, if I have an even number here, you're going to need these have to either both be odd or both be even. So since this one's going to be an even 20, what is 20 plus 12? 32. 20 minus 12, 8. Let's just to be sure again, negative 20 plus or minus the square root of 32 times 8. Okay, just think if I move over a 2, I've got 16 squared. So obviously that's going to be 16. You have an even plus an even. Gonna work out fine. So when I make an even here, it's definitely even times even because you're subtracting an even from k both times. If k was an odd number and I subtracted an even, I would get an odd times an odd. So we are going to be okay because that is going to produce an odd number, and when you square root the odd, you get an odd, but you have an odd here. Again, the format is odd plus or minus odd over 2. Of course that's going to be even. An odd plus an odd or an odd minus an odd will be even. Gosh, that's an awful lot of reasoning for problem number 7 on the 10B. Again, this is why I felt like this test is a little bit harder than the A test was, and you can probably expect lower cutoffs on this test. Okay, so you're going to get these 4 values of k, but they're plus or minus for each one. Total number of values is 8. Let's get to problem 8. And now for the last one of this rapid fire set, the 2022 AMC 12B problem 5. The point -1, -2 is rotated. Already, I want to see a picture. Where is -1, -2? There's -1, -2, right about there. Is rotated 270 degrees counterclockwise. So counterclockwise is this way, but that would be the same as 90 degrees clockwise, right? So if we go 90 degrees clockwise, about what point? The point 3, 1. 1, 2, 3, 1. Then I'm going to connect to this point, and you're going to rotate 90 degrees this way, clockwise. So let's think about how this could work. We've got 3, 1. We'll get rid of that so we can kind of see what's going on here. 3, 1, this is -1, -2. So think about perpendicular lines. They're going to have negative reciprocal slopes. So I'm going to go from -2 to 1, that's a rise of 3. -1 to 3, that's a run of 4. I'm going to need -4/3 to be the slope from here. I would normally go down 4/3, but because we're going back that way, I'm going to subtract 4. or go up 4 and over 3 to the left. So usually I would go down 4 over 3 to the right to continue, but I'm going to go up 4 and 3 to the left. So then that's going to be, if I go up 4 from here, I'll be put at the point 5 for y. 3 to the left would be 0 for x. As one last quick check to make sure we don't make a mistake, let's just check the slope. 5 minus 1 is 4. 0 minus 3 is negative 3. I want to make sure that when I go here, 1 minus negative 2, that's the rise, over 3 minus negative 1. If you multiply, you get negative 1. The answer is B. Let's get to problem 6.